Hi, my name's Joey, and I am a sophomore in industrial engineering here at Iowa State. And we are here in the WISE office today. And WISE stands for Women in Science and Engineering, right behind my head. And that's a program here at Iowa State to support women in science and engineering. And some of the services they offer are study groups, mentoring, and then we also do this K through 12 outreach that we're doing with you today.
Hi everyone, my name is Tiara Turner. I'm also an industrial engineering student. I'm a senior here at Iowa State, and just to give you a little bit of background, industrial engineering deals mostly with processes and improving people's day-to-day lives and work. So whether that is looking at logistics, so how things move through a plant or throughout its supply chain, or looking at quality improvement, so how can we make a product better or how can we make it easier to manufacture. There's a long list of things that we're doing in industrial engineering. I'm going to be working for Kraft Heinz this summer. They make the ketchup and the mac and cheese. And one of my career goals is to try all the products so that way I can have a better idea of how to improve the foods that we eat and make the world a better place.
Today we are going to be learning about the different properties of water, such as cohesion, adhesion, and surface tension in an activity called wet pennies.
Awesome. So the way that we're going to be looking into those three properties is that we're going to be filling our cups up with some water, and then we're going to add paper clips to them to see how many paper clips are needed to overflow the cup. And then we'll also be putting droplets of water onto coins. We'll be looking at the penny and the quarter first, and then if we have additional time, we'll move into the nickel and the dime. We're going to be seeing, how many drops can fit on their surfaces. And so with that, we're going to do a materials check. So before we get started, be sure to check your area, make sure it's clean surfaces, and also to make sure that you have all of these items. First and foremost, you're going to need different coins, a penny, a quarter, and then also a dime and a nickel. And then also you want to have a piece of paper and then a pen. You're also going to want to have paper towels, a clear glass or a plastic cup that is clear, a water dropper, and also a regular cup and some water. Hi, so right now we have our cup filled with water, and we just filled the cup to the top ever so slightly before the point of overflow that we thought. So use your best guess or your best sense of judgment to gauge just how much is enough water before it's already overflowing. And before we began to put paper clips into the cup, we decided to make some predictions. Joey predicted 15, and I predicted 11. I just took the paper clips in my hand and shook them around, and I guess 11. I think that's how many will cover the bottom before they start to topple over.
I was just visualizing how many would cover the top instead of the bottom, so we'll see. You want to make sure you're counting. I'm just going to do tally marks over here, how many paper clips as you're putting them in. So as Pierre's putting them in the cup, I'm just going to be marking off as she does that.
We just reached 15 paper clips, and that is the point at which that was the larger of our two predictions. If you too have reached the point of your largest prediction amongst your group or just with yourself, then this will be a good time to take a pause and come up with a new prediction. So determine what do you think, how many more paper clips do you think will it take to overflow your cup based on the prediction that you made and the state of the cup now. And we'll do the same.
So our new predictions are now 30 and 37. So we'll see if we are right.
All right, so far it appears that the water has kind of an inverted meniscus effect, like the little curvature that's at the bottom of water once you pour it. Kind of like a bubble up. That's the roundness over the top that kind of makes it look like a lid.
We're currently at 137 paper clips.
So kind of 37. Just kidding. But still no overflow. That drop of water happened prior to us.
We are going to continue and fill our cup up with paper clips until it overflows. Now would be a great time to pause the video and do the experiment yourself. Use our starting as an example and see how many paper clips it takes to overflow your cup. Make a prediction ahead of time and then record your results.
Our cup finally overflowed on the 437th paper clip. So, as you can see, we didn't continue to update our predictions, but as you continued to put paper clips in, you could have continued to update your predictions as you went further.
Did you expect that there would be that many paper clips?
Not at all. Not at all.
Me neither. Now we're going to talk about cohesion and adhesion. Adhesion is what's going to be holding the water droplets to the surface of the coin. So we have put water into this nice dropper, and we have both our penny and our quarter.
So before we start adding drops to the coins, we are going to make predictions on how many drops each coin can hold. Predictions for the penny are 50 drops and 37. Our predictions for the quarter are 278. So we'll see how this turns out.
Woo.
We are now going to conduct the part 2 experiment by adding 1 drop of water at a time to each coin and counting. Now would be a great time to pause the video and do the experiment. Make sure to make a prediction ahead of time, and we will be conducting these results 3 times on each coin and then calculating the average. Also, if you have other coins, such as nickels and dimes, that you would like to try, you can go ahead and do those as well. Now take a look at our results. Is this similar to what you found? As you can see, the average number of drops was almost double that of the penny of the quarter. Now that you have been able to complete the experiment, take some time and answer these discussion questions. When you are done thinking about your answers, you can continue watching the video to hear our discussion.
Awesome. So we just had a really fun activity that we got to go through. Hope you all had a good time dropping the water droplets on the coins and learn a bit of patience with the paper clips and the cup of water. But some of the 3 forces that we just observed that were tugging on that water were gravity, cohesion, and adhesion. And essentially, gravity was the force that was flattening the droplets. So if you noticed with the coins and you're dropping them, and even when you were putting the paper clips in the cup of water, there was sort of a little bubble over it. With the coins, however, the drop that allowed it to kind of overflow, that was the flattening force, which was gravity. And then cohesion is what holds those drops together. So you might have noticed that when you were dropping the water on the coins, that no matter what, they were sticking together. They weren't spreading out, so to speak. They were kind of holding and just growing, even growing in height. And then adhesion is what allows the water to stick to the surface of the coin. So it's what was pulling the water kind of to the center and holding it to the coin itself. And then of course you had the forces kind of overtake, the gravity force overtake that to allow it to overflow. Cohesion, going back to cohesion, what keeps the water droplets together. Essentially, water molecules are going to be attracted to other water molecules just because they're one and the same. So, kind of different from magnetic forces that where opposites attract. With the water molecules, they attract one another, and the oxygen in, of the water has a negative charge, and the hydrogen has a positive charge. So essentially, the negative end of one droplet is going to be looking to attract the positive end of a different droplet, and that's what allows the cohesion to occur. And then also the hydrogens of one water will also be looking for on the flip side, the oxygens of a different water droplet. And so that's kind of that attractive force that's similar to magnetic forces that are happening within the molecules themselves that allow like molecules to attract one another.
Surface tension is the name that we give to the cohesion of water molecules at the surface of a body of water. The cohesion of water molecules forms a surface film or skin, which you could see in our video, the bubble that was created at the top of the penny and the cup of water when we were doing the paperclip experiment. Some substances may reduce the cohesive force of water, which will reduce the strength of the skin, which is what held the water together before it overflowed.
So one way to further this experiment, if you have some additional time, is to look for some soap that you might have, hand soap or dish soap, in your kitchen or bathroom, and add a little bit of that soap to the water that you were using to drop the droplets onto the pennies, and just observe how that might impact the cohesion that you talked about. So the film or the skin-like portion of the molecule. What we suspect would happen is that because of the nature of soap, that it would actually break down those water molecules and allow for less cohesion. So they'd be less likely to attract one another because of the components and the properties of the soap itself, not allowing the water to find those opposite charges to attract to itself. From a more scientific perspective, essentially those soapy drops are going to be reducing the cohesive force and breaking down the surface tension that exists in that water. And also the soapy bubbles or soapy droplets are going to be a lot smaller than those of the water droplets, simply because that's the nature of the soap, producing those smaller bubbles. And so what that essentially means is that it would take way more soapy water drops than it would just regular plain water drops to fill a penny or any other surface that we've dealt with today.
Okay, so some real life examples of these forces is rain. So you see when it rains outside that water falls down in droplets and not individual molecules or large clumps of water, I guess, if you want to call it that.
Not a splash.
Yeah, there you go. And that's because of cohesion and its ability to attract different water molecules to each other. Another example, have you ever seen bugs just sitting on top of the water? That's because of surface tension. So their ability to live on top of the water is them taking advantage of that property of water.
Well, thank you so much for tuning in with us. Again, my name is Tiara.
And I'm Joey.
And we hope you have fun with wet pennies.
Bye.